Okay, let's unpack this. We've got a stack of notes and diagrams here, diving into some really fundamental ideas in geometry.
Mm-hmm. Symmetry, reflection, and rotation.
Exactly. And think of this deep dive as, a way to quickly grasp how shapes and points move and relate in space.
Yeah, it's really about figuring out the how and why behind things lining up or flipping over or spinning around.
Right. So our mission here is to pull out the core nuggets, the rules, the examples, those aha moments.
So you feel instantly a bit more clued in on these topics.
First up, symmetry. Specifically, linear symmetry.
Okay.
The basic idea. Super simple. If you can fold a figure along a line, and the two halves just match up perfectly.
Then it's symmetrical about that line.
Yeah.
And that line is the line of symmetry, or sometimes called a mirror line.
Right. And what's really interesting is why that works. I mean, the sources show examples like folding paper and cutting a shape.
That crease you make. That is the line of symmetry. It's about every point on one side having like a matching point on the other side.
At the same distance from the line.
Exactly. Equidistant. Which explains why a line segment is symmetrical about its perpendicular bisector.
Makes sense. And an angle with equal arms. Symmetrical about its bisector. Same logic.
Triangles give us a few different scenarios, though, an isosceles one.
Just one line of symmetry, right? The bisector of that main vertex angle.
Mm-hmm. But an equilateral triangle, being all equal, it gets 3 lines, one through each angle bisector.
And here's where it gets really neat. Regular polygons, they follow this beautiful pattern.
Oh, yeah.
The number of lines of symmetry. It equals the number of sides.
No way. So a square has 4.
4 lines. A regular pentagon, 5. Hexagon, 6. You see this pattern because they also have rotational symmetry, and those lines often connect, opposite points or midpoints.
So that's cool. And it even shows up in, like, the alphabet.
Totally. Letters like A, C, D, E, lots of them have one line. H, I, O, X have 2.
And some have none, like F, G, J.
Right. The sources mention N has 1 line, which is interesting. And a circle. Forget counting.
Infinite lines. Any line right through the center works.
Okay, moving on then. Reflection. The sources give us a pretty concrete way to think about this, especially using coordinates.
Right. So at its core, reflection across a mirror line means the image, the reflected point, is the same distance away from the mirror as the original.
Just on the opposite side.
On the opposite side. And the mirror line itself is the perpendicular bisector of that imaginary line connecting the point and its image.
Which translates really nicely into coordinate rules. Reflecting a point pxy in the x-axis gives you what?
Px. So think about it. The x-coordinate, your left-right position, that stays the same when you flip over the horizontal x-axis. But the y-coordinate, your up-down position, it keeps the same distance but flips direction. So positive becomes negative, negative becomes positive. The sign changes.
Okay, got it. So reflecting the y-axis must be similar then.
Exactly the same logic. Pxy goes to pxy. This time, the up-down y stays the same, but the left-right x flips sign.
And reflecting in the origin. Both change.
Both change. Pxy maps to pxy. It's kind of like doing an x-axis flip and then a y-axis flip.
All right, finally, let's touch on rotation. The sources focus on rotating around the origin, mainly specific angles.
Rotation just means moving a point in a circle around a fixed center. Here, it's the origin, 0, 0.
So a 180-degree rotation about the origin, if you take pxy.
It rotates to pxy.
Hang on a sec, pxy. Didn't we just say that was reflection in the origin?
We did, and that's a really key insight here. A 180-degree rotation about the origin gives the exact same result as reflecting through the origin.
Wow. Okay, so different actions, same outcome.
For that specific case, yeah, shows how these transformations can be linked.
That's fascinating. Okay, what about 90-degree turns? Say 90-degree anti-clockwise.
Okay, pxy rotates to pyx. Notice the coordinates swap places.
They swap, and the new x-coordinate gets the negative sign.
Right. Visualize it. The original y distance becomes the new distance along the x-axis, but on the negative side.
Okay.
The original x distance becomes the new distance up the axis.
Okay. And 90 degrees clockwise must be related.
It is. Px. Y goes to pyx. Coordinates swap again, but this time the new y-coordinate gets the negative sign.
Swap, new y gets the minus.
Oh.
Got it. Follows the same kind of visual logic. So let's wrap this up. We've seen how figures can have that internal mirroring, which is symmetry.
And how we can flip points and shapes across lines or points, that's reflection.
And then turning them around a point rotation.
Yeah, and these aren't just, abstract math ideas. They're literally everywhere. You see them in nature, art, architecture.
And definitely in things like computer graphics, engineering. the building blocks are these transformations.
Absolutely.
And that link we found between rotating 180 degrees and reflecting in the origin, that's really interesting.
It is. Are they fundamentally the same thing, just viewed differently? Or is it just a coincidence of the coordinates?
Good question. Something for you to maybe ponder until our next deep dive.